So before we get into the physical properties of carboxylic acids, let's talk about unsaturated carboxylic acids. That's just a carboxylic acid that has a double bond in it. So if you've got something like this, here's the carboxylic acid group, and you've got something, for example, like this, and I'll put in all the hydrogens. Okay, so you can see that you've got a double bond here and you have a carboxylic acid group. It's going to be named as an acid, but you have to tell everybody that there's an ene group there, the double bond. You have to tell me where that double bond is. So obviously this is carbon 1 because the carboxyl group is always carbon number 1 in a carboxylic acid. So 1, 2, 3, 4, 5, 6. So the double bond is between carbons 4 and 5. So you have, if this was just an alkene, it would have been 4-hexene, or actually we would have numbered it the other way. It would have been 2-hexene. But the double bond does not take precedence here. It's the carboxylic acid group that has a higher priority. So you have to name it. It would have been hexanoic acid if it didn't have the double bond, but because it has the double bond, it's hexenoic acid. You got to tell me where the double bond is. So that's 4-hexene. Notice that? Oic acid. So instead of hexanoic acid, it's hexenoic acid. That's all you need to know about unsaturated carboxylic acids. All right, so physical properties, again, we're talking solubility and boiling point. Solubility is all about potential hydrogen bonding with water. Do we have some polarity here? Do we have an ability for this molecule, whatever it is, to hydrogen bond with water? Yes, this can hydrogen bond over here. These lone pairs can attract a hydrogen from water. So there are several sites where there can be some hydrogen bonding. If you've got a short carboxylic acid, 1, 2 carbons, no problem. They are soluble, or another word for soluble is miscible. They are soluble in water. But the minute you start increasing this carbon chain, then it's not as soluble anymore, all right, because it becomes very nonpolar, and this isn't enough to get it into solution with water. The other physical property is boiling point. Remember from previous chapters, boiling point is all about intermolecular forces. You can see that carboxylic acids, you had this carboxylic acid in a beaker and you had like a whole million of them. It has potential hydrogen bonding, so they can hydrogen bond with each other. Why? Because there's a hydrogen attached to an oxygen. So you can have intermolecular hydrogen bonding. You can have dipole-dipole. And you can have London force, obviously, because everybody does London force. So if you have a beaker of a carboxylic acid, a beaker of an alcohol, and a beaker of an aldehyde, and they had the same molecular weight, which do you think would have the highest boiling point? Well, you can see, if you just look at the functional groups, this would be what an alcohol would look like. And then this is your aldehyde. Okay, so beaker 1, beaker 2, beaker 3. This can do hydrogen bonding, intermolecular hydrogen bonding, dipole-dipole, and London force. So can this, intermolecular hydrogen bonding, dipole-dipole, and London force. This one cannot do intermolecular hydrogen bonding because there's no hydrogen bonded to an oxygen. So this can't do any intermolecular hydrogen bonding. Aldehydes and ketones can't, remember. But it can do dipole-dipole and London force. So obviously this is going to have the lowest boiling point. These two guys now, how do they differ? Well, if they have the same molecular weight, they'll have about the same London force. But you can see here that there's more potential for hydrogen bonding here than this one. So this will have a higher boiling point than this. This one will have a higher boiling point than this. Okay? Always try to compare different functional groups when you're studying. because that way you get the fuller picture here. All right, so that's it for physical properties. The next thing on our what you need to know list is how to prepare carboxylic acid. Remember, the term how to prepare means how do you synthesize a carboxylic acid? How do you make it? Well, we already know that if you start off with a primary alcohol, if you oxidize it, let's put an O in parentheses, any oxidizing agent, you can turn it into an aldehyde, and then that gets turned into a carboxylic acid. So you can have two starting points to end up with a carboxylic acid. You could either start with a primary alcohol, you could eventually get there, or just go ahead and start with an aldehyde and you'll eventually get there, all right? If you start off with a secondary alcohol, you're not going to make it to a carboxylic acid. Secondary alcohol, remember, gets oxidized and turned into a ketone, and ketones aren't oxidized and turned into anything. So the only way you can get a carboxylic acid is starting off with a primary alcohol or starting off with an aldehyde and using an oxidizing agent. And that covers preparation of carboxylic acid. Okay, so now that we've talked about that, we're ready to talk about how a carboxylic acid behaves as an acid. If you remember from intro chemistry, the Bronsted-Lowry theory of acids and bases is that acids are substances that donate a proton. So our carboxylic acid has an acidic proton to donate. So let's take a look and see what that looks like. Here's the carboxylic acid. Let's say I've got ethanoic acid or acetic acid. Ethanoic acid would be the IUPAC name. Acetic acid is the common name. And let's put our lone pairs here. This right here, let me use a different color. This right here, this is the acidic hydrogen. These hydrogens over here are non-acidic. What does that mean? That means they are not donated as protons. They are not going to leave the molecule. This one over here can. It will be donated. Now, carboxylic acids are not strong acids. They are weak acids. Remember how phenol was a weak acid? All organic acids are considered weak acids. If you remember from intro chem, the only strong acids are hydrochloric, hydrobromic, hydroiodic, sulfuric, perchloric, and nitric, and then in some books also chloric. But all these acids that we're talking about are not considered strong, meaning that they don't donate their proton 100%. It's just partial hydrolysis here, partial dissociation. Okay, so how does it donate the proton? Let me show you. So if you have a molecule of water here, this hydrogen ion will go over to the water, making it the hydronium polyatomic ion. And then what's left over is this over here. Actually, don't worry about the lone pairs because I don't want them to confuse you. Here we go. So this here is what is left over. If this was called acetic acid, this is called acetate. Look how we changed the name. If this was called ethanoic acid, which is the IUPAC name, this is now called ethanoate. Notice how the name changed. We got rid of ic acid and we added the suffix ate. Okay? We got rid of ic acid, added the suffix ate. So this ion is always going to have a negative charge. If you have two carboxylic acid groups, you're going to have a -2 charge. One carboxylic acid group, a -1 charge. So these carboxylic acids, all of them can donate a proton to water, or they can all be involved in an acid-base neutralization reaction, as we're going to be seeing in a little bit. All right, so we talked, oh, this, by the way, this is called the carboxylate ion. Carboxylate ion. So this is the carboxylic acid, this is the carboxylate ion. Naming the carboxylate ion, you get rid of the ic acid and you throw in the suffix ate. Okay, so if you had hexanoic acid, it would be hexanoate. If you had butanoic acid, it would be butanoate. If you had butyric acid, common name, it would be butyrate. All right, so that's naming and identifying carboxylate ions. We're going to do acid-base neutralization reactions and create salts in the next video. Okay?